Today we will start on a new module. Earlier we have looked at state space search, and you also have looked at logic, propositional calculus and first order calculus. Today we will look at a new module which comprises planning problems. So today we will give an introduction to the planning problem, and in the subsequent lectures we will look at different algorithms which efficiently solve the planning problem. The instructional objectives of today's class is: the student will get an introduction to planning problems. Given a situation which warrants planning, they should be able to formulate the planning problems in terms of the representation formalisms that we will discuss. Today we will look at the strips formalisms as well as situation calculus and certain other techniques. The student should be able to cast planning problems as search problems, and they should be able to cast it as a normal state space search problems. But we will also explore why state space search solution techniques are not ideally suited for solving planning problems, and we will discuss what other techniques can be used for searching in the planned space. So this is a schematic overview of the intelligent agent that we discussed in the beginning of this course. If you remember, this is an agent, this is the environment. The agent interacts with the environment. For simplicity, initially we will assume, at least for this course, we will assume that the environment is static and the environment is fully observable. The agent receives perceptions from the environment through its sensory apparatus, and we assume that this perception is perfect. That is, the environment is fully observable to the agent, and the agent can take actions through its effectors which can change the state of the environment. We will consider only deterministic actions. In the planning problem, we will assume that the agent has a goal or goals that the agent wishes to achieve, and given the goals, the agent wants to find a sequence of actions that would let him or her achieve the goals. And the sort of question that we will ask is, given the current situation, what is the next action, or what is the next action sequence that the agent should take? So in planning problems, the task of the agent is to synthesize goal-directed behavior, and the agent will have a goal which the agent wishes to, the agent has a goal which the agent wishes to achieve, and the objective of the agent is to select a sequence of actions, let us say A1, A2, A3 up to AN, so that as a result of executing the actions in this sequence, the agent will get to a state where the goal is achieved. And while determining the action sequence, the agent would have to consider the causal dependencies between the different actions. And as I mentioned, for today's class and for our planning lectures, we will primarily restrict ourselves to deterministic and fully observable environments. There are other types of planning problems where the environment may be stochastic, the environment may be only partially observable, the actions may have non-deterministic effects, and in such situations, in stochastic environment, it may not be possible, or it may not be the best situation for the agent to plan a sequence of actions. Rather, the agent might like to determine a policy so that he can determine his current action and based on the feedback received at the next state, the agent can decide the subsequent actions. But for the deterministic and fully observable situations to which we will confine ourselves today, the solution to the planning problem would be a sequence of actions that achieve the goal. Now let us try to understand why planning is important and where planning situations arise. This course is about intelligent agents, and intelligent agents need to operate in the world, and to operate in the world, the agent should be able to take actions. The agent should be able to take actions which are appropriate for the situation that is at hand. It should also be able to take actions that change the state of the world so that the world achieves the goals that the agent wishes to achieve, they can be achieved in the world. And additionally, the agent will like to compose more than one action, a set of actions together to achieve complex goals. So, in order to change the world to suit the needs, agents will need to know the behavior of the world. They need to know how the world changes as a consequence of the different actions that can be taken in the world. And reasoning from this, the agent should be able to formulate a plan to take to achieve its goals. And in this case, while dealing with planning, the agent needs to reason about dynamic environments, because as the agent is taking an action, the action is usually changing the state of the world. So in the dynamically changing world, the agent has to reason about the effects of its action sequence. Let us look at a very simple example of everyday example of a planning problem that we have to often tackle. Actually, a lot of problems that we tackle in our everyday activity or in the long-term goals are planning problems. For example, suppose my plan is to have a birthday party at my house tomorrow, and suppose the current situation is that I am at home, there is flour at home, there is no butter, there is no sugar, and I want to find a sequence of actions or a plan so that I can hold a birthday party tomorrow. And this may be the sequence of actions that I wish to perform that would lead to the realization of that goal. I invite friends, I go out and buy butter, I go out and buy sugar, I buy balloons, I decorate the house, I bake the cake, and so on. So this is a sequence of actions that I carry out which realizes the objective that I have in mind. Agents or robots often may need to plan. Their planning is involved in a lot of everyday activities that we do. For example, if we want to navigate and if I want to get to this room, I have to plan how I would come to this place starting from my office. Or if I want to deliver this course, I have to plan the sequence of lecture materials that I will deliver to achieve the objective of teaching this course. So planning is a part of everyday activities like communication, like navigation, as well as many other activities. Let's look at some applications of planning. Mobile robots. In fact, mobile robots were one of the initial goals of AI, and mobile robots need to do planning on a very large scale for navigation, for task planning. So different types of planning are involved for mobile robots. Autonomous agents also need to do planning. For example, NASA uses a deep space planning agent. We have earlier discussed about the different rovers that have been sent to space, to Mars, and these agents are involved in autonomous planning. In simulated environments, goal-directed agents are needed for training, for playing games, In web and grid environments, planning is needed for composing queries or services to deliver a particular service. In education or tutoring system, planning is required to decide what material to deliver next to the student. Planning is also used in scheduling problems where we have to make choices of actions as well as we have to handle different resources. Hubble Space Telescope Scheduler is an example of a very useful system which uses planning. Actually, nowadays planning and scheduling go hand in hand. Then workflow management is a place where we need planning. Planning has been used in software test case generation, in plan-based interfaces and many such applications. So let's see what is the essence of a planning problem. In a planning problem, we are given a way to describe the world. We are given a description of the initial state of the world, and we are given the description of what the goal state should achieve. And our objective is to find a set of possible actions which, when executed in sequence, will change the world so that a goal can be achieved. Or rather, we are given the initial state description, the goal description, and the description of a set of possible actions that are there in the world, and we also know the effects of these actions. And our objective is to find a sequence of actions or prescribe a sequence of actions that will change the initial state and take the agent to a state where the goal will be achieved. Now, planning problem, there's a lot of logical structure in the way a planning problem is formulated, and our objective in designing planning algorithms is to design algorithms that take advantage of the logical structure of the problem description. And in order to be able to do so, we need to be able to represent the problem in a suitable logical language. Now let us see following a very common formalism of representation of planning problems. Let us see how the states, the actions, goals, etc. are represented. So in a planning problem, typically states are modeled in terms of propositions or state variables or features of a state. So we have different propositions, and in a particular state, these propositions have different binary values. For example, suppose the propositions are at home, have sugar, have butter, have money, etc. And the values of these propositions may be true or false in a given state. For the initial state, we have a complete description of the state. We know which are the propositions which are true in the initial state. And typically, we have a partial description of the goal state. We want to know what are the propositions that we want should be true in the goal state. So a state is typically represented as a conjunction of positive literals. So we have to specify the propositions which are true in a particular state. This will fully represent the description of a state. For example, a state could be lighted and hot and made of brass. We can also use propositions as a conjunction of propositions to represent a state. We could also use first order literals. For example, we could use at robot 1 kitchen and at robot 2 garden. Now notice that this is a predicate, at is a predicate, but the arguments are ground literals. So we allow first order literals to be used to describe a state, but these literals must be ground literals and they must be function free. So literals must be ground and function free, which means that we cannot use things like at home, at father Fred home. So, this sort of first order literals are not allowed because here we have a function. We also do not allow quantifications, that is, we do not allow at x home, where x is a variable which is either existentially quantified or for all quantified. So, these sorts of first order literals are not allowed, but we can have ground first order literals as in at robot 1 kitchen. So, in a simple formalism, we allow states to be represented as a conjunction of propositions or a conjunction of first order literals or a mixture of them. Now, there could be a large number of literals or propositions that are part of the planning problem. We may specify the values of some of the literals. For example, we may specify that lighted is true, hot is true, made of brass is true, but we may not have specified the values of the 20 other literals that occur in this planning problem or 100 other literals that occur in this planning problem. In the closed world assumption, we will assume that any condition that we have not mentioned are assumed false. So, in a closed world assumption, we will say that whichever literals we have specifically stated to be true in a particular state will be true, the other literals will all be false. How is goal represented? A goal is represented as a partially specified state. For example, rich and famous and stays Mumbai. This is a description of a goal. We say that a state S satisfies a goal G if the state S contains all the proposition of goal G. So, suppose the description of the state S is lighted and hot and made of brass. So, this state satisfies the goal lighted and hot, because the propositions lighted and the proposition hot both occur in the goal state. If we take another example, if we say that rich and famous and miserable and stays Mumbai and acts in movie M1, so that state will satisfy the goal rich and famous and stays Mumbai. So, for a goal to satisfy a state, all the propositions in the goal must be in the description of the state. So, when we model planning problems, states are modeled in terms of propositions, as we said, complete initial state and partial goal state. Now, we will look at how actions are modeled. So, actions are typically modeled as state transformations. To specify an action, we specify what transformation to the state space will be brought about by the execution of an action. So, to represent actions, different formalisms have been used. Today, we will discuss about strips, which is a classical formalism for describing actions. We will later describe ADL, which is a more modern language, which is less restrictive language, which has better expressive power than the strips representation formalism. So, in strips, actions are specified by specifying two things. One is the precondition of the action, the other is the effect of the action. The precondition of an action means the condition that must hold so that the action can be executed. Now, suppose I want to pick up an object. The precondition is that my hand must be empty and the object which I wish to pick up must be portable, must be available in front of me. So, preconditions denote those conditions that must be satisfied so that the action can be executed. Secondly, we need to describe the effects of an action. What will happen? How will the state change as a result of taking the action? Now, suppose the agent is in a state where certain propositions are true. Now, when the agent executes an action, the state may change. The change can be described by using two different things. Some of the propositions which were true earlier would not be true after the action is executed, and some new propositions which may have been false earlier would be true when the action is executed. So, suppose let us take an example of an action fly, which takes three arguments: fly P from 2. The precondition is that at P from can fly P, airport from and airport to. So, if these four conditions are satisfied in the previous state, then only this action can be executed. And as a result of executing this action, at P from will no longer be true, but at P2 will now be true in the next state. So, the effect of an action is described by a conjunction of positive and negative literals. Negative literals correspond to those propositions which have to be deleted from the previous state to get the current state. The positive literals denote those propositions that will have to be added to the new state. Now, the other assumption that we will make is that the rest of the propositions that we have not specified in the in the effect list, those propositions, their status will be unchanged. If the other propositions were true in the earlier state, they will continue to be true in the current state. If they were false in the earlier state, they will continue to be false in the next state. Now, look at the action fly P from 2. Now, P from 2, these are not ground literals, these are variables. So, fly P from 2 represents an action schema. An action schema can represent a number of different actions. For example, it can represent the action fly plane 1 Kolkata Delhi. It can represent the action fly plane 1 Kolkata Chennai. It can represent the action fly plane 1 Kolkata Delhi, fly plane 1 Delhi Kolkata, fly plane 1 Delhi Chennai, fly plane 2 Kolkata Delhi, and so on. So, this action schemata can represent a class of actions, a number of different actions. The precondition of an action is a conjunction of function-free positive literals. They denote what must be true in a state so that the action can be executed in that state. This action fly P from 2 can only be executed if can fly P is true, P is at from is an airport, 2 is an airport, then only. So, these are the conditions which have to be true so that the action can be executed. All actions cannot be executed at this state. For example, if P is at from, I cannot execute the action fly P to from in the current state. As a result of the action, the effect of the action is specified by the effect clause. The effect says not at P from and at P2. So, the effect is a conjunction of function free literals, not positive. So, this is a mistake. So, effect is a conjunction of function free literals which may contain a set of positive literals and a set of negative literals. And they together represent how the state change when the action is executed. If I have a negative literal, it means that proposition is to be removed from the previous state to get the current state. If we have a positive literal, it means that proposition has to be added to the new state. Now, actions represent change in the world. An action changes the world. When we consider, we want to know how an action will alter the world. We also want to keep track of the history of the world states and answer questions about potential world states. In order to do that, we need to reason about actions. Now, you have studied first order predicate calculus earlier in this course. Today, we will briefly talk about situation calculus, which is a formalism in first order predicate calculus, which allows us to reason about time and reason about situations. Situation calculus was first discussed by McCarthy. It is a formalism to model dynamic worlds within first order logic. So, situation calculus is a formalism to model dynamic worlds. The key idea in situation calculus is that we represent a snapshot of the world which we call a situation explicitly. And these situations index the different states of the world. The states of the world change with time. Initially, suppose the world is in a situation S0 which has a particular state. Then when the agent takes an action, as a result the state changes and S1 is the new situation. And we see that as a result of taking an action, the situation changes. That is, actions map situations to situations. Fluents are properties that change from situation to situation. There are certain propositions which do not which are independent of the situation, but there are certain fluents are those that change from situation to situation. So, in order to specify those propositions, we need an extra argument to denote the situation. For example, suppose let us take a proposition on. Suppose we have a blocks world. A blocks world is a world where we are dealing with several blocks, and our objective is that suppose we have a particular configuration of the block, we wish to move these blocks so that we get to some other configuration of the blocks. So, this is the block world. In the block world, a typical proposition that we use is whether a block is on top of another block. For example, we would like to say on AB. Now, on AB, this proposition holds in this state or in this situation, it does not hold in this situation. So, in this case, we will specify with an extra argument that on AB, suppose we call this situation, S1, we call this situation S2. So, we can say on AB in situation S1, on BA in situation S2, and not on AB in situation S2. So, on is a proposition which whether on AB is true depends on the situation. So, we use a new situation argument in this proposition. Then let us take the proposition clear. So, clear is also a proposition which is so clear A, whether A is clear or not depends on the situation. Like in this case, A is clear A in S1, but A is not clear in S2, C is clear in S1 2. So, again to continue with the blocks world example, so here I have a situation which we call S0, and we see that in this situation B is clear. So, clear B S0, on B C S0, clear A S0, and this is a robot hand, and we have a proposition corresponding to hand empty. So, hand empty at S0. So, this is the description of this state in the blocks world. Now, let us look at possible actions in the blocks world. Let's take a particular action, pick up. So the action pick up X is the schema, is the action schema. Pick up B is a particular instance of the action schema. Now suppose the agent executes the action pick up B in the situation S0. So we denote it by do pick up B S0. So this action is executed at situation S0. The new situation, that is, so do pick up B S0 represents a new situation which arises out of executing the action pick up B on situation S0. So do pick up B S0 results into a new situation S1. Okay. So in the situation S1, on BC will not be true. So not on BC in S1. Clear C S1. So clear B will not be true, but clear C will hold true in situation S1. So S1 is a new situation which is a result of executing the action pick up B in situation S0, and the situation S1 can be described by clear A, clear C, not hand empty, and not clear B, and not on BC. This is another example. Suppose the situation S0 corresponds to at home S0, color door red. Now notice that this proposition color, its value does not depend on the situation, depend on the time. So for the proposition color, we have not added the situation argument. At is a proposition whose value changes depending on the situation. So here we have added a situation argument, but for the proposition color, we have not added any situation argument. So S0 is described by at home S0, color door red. Now S1 is a situation which the agent gets to if the action go store is executed. So S1 is a result of, so S1 is a result of executing the action do go store, action go store in the situation S0, and the situation S1 is described by not at home S1, at store S1. So this is the effect of the action go store, not at home and at store. This proposition color door red is not affected by this action go store. So if color door red holds in situation S0, it will continue to hold in the situation S1. Now, there could be in the initial state, there could be a, so as the entire problem description could have hundred or several hundreds of different propositions, some of which hold in the initial state, some of which hold in the, do not hold in the initial state. Now, after every action we get to a state, and if we have to describe whether each of these propositions are true or false in that state, that will be a very laborious process. And we also notice that typically an action only has a local effect, it only changes the value of certain propositions. So the vast amount of background information remain unchanged. This problem in AI is referred to as the frame problem. For example, suppose I am at home and there are different situations, different propositions that hold and the current time. For example, my son is at home, the store sells bread, my age is 38, and then so many other things which some of them hold in this state, some of them do not hold in this state. Now suppose I execute the action go store. Now what will change is that at home will no longer hold and at store will hold. However, this vast amount of other propositions, that they will continue to have the same value as they had earlier. So this background information does not change. This is known as the frame problem in AI, and we want an efficient representation of this frame problem. And if we confine ourselves to the framework of logical reasoning, then we have to capture the frame problem, we have to capture it using a set of rules. And these rules, this can be captured by a set of axioms which we call the successor state axioms. So, successor state axioms encode the fact that normally things stay true from one state to the next unless an action changes them. For example, suppose you consider the proposition at x. Now, at x will hold at a next situation which has arisen out of doing the action A in situation S. So, do AS is the new situation which the agent finds itself in after carrying out the action A in situation S. At x holds in this situation if and only if either A equal to go x, if the current action is go x, then after this action at x will hold, or at x will hold if the action is not go y and x is already at s. Sorry, the agent is already at x in the previous situation. If the agent is already at x and it does not execute a go action, then the agent will continue to be at x. Or if the agent does execute the go x action, then at the next situation it will be at x. Otherwise, the agent will not be at x. So, which means that for every action, or rather for every fluent, every proposition that depends on the situation, for every fluent we have to add one axiom like this axiom, which we call the successor state axiom. So, in this case the fluent at x only changes with the action go. There could be a fluent which changes as a result of more than one action. Suppose it changes with 3 different actions. So, the successor state axiom for that fluent would involve all these 3 different actions. Now, once we have written out the problem in this form, once we have written the initial states, the action representations and the successor state axioms, then we can use theorem proving to find a solution to the planning problem. You have already seen how theorem proving works. Theorem proving can be used to find a solution to the planning problem. However, theorem proving may not always be a very efficient method of solving the planning problem. So, what we will do in this class is to explore different direct methods of solving the planning problem. So, we first look at strips, representation for action in strips. We have talked about a little bit on strips earlier. So, strips, every action is represented by the preconditions of the action, which is a list of propositions that have to be true for the action to be executed, the delete list and the add list. So, an action, the effects of an action in strips are divided into 2 different lists. The add list is the list of propositions that become true after the action is executed. The delete list contains a list of propositions that will become false after the action is executed. In the strips formalisms, actions specify all the state variables whose values are changed by the action, but strips places certain restriction on the type of on the precondition list as well as the add and delete list. Specifically, strips does not allow disjunctions in the effect list, that is in the add or delete list, and strips only allows propositional preconditions and effects. We will later see that there are some other languages like ADL which relax this criteria a little bit. So, let us look at an example problem Suppose the initial state is described by at home, not have banana, and not have money. Not banana, it should be money. And the goal is have banana and have money and at home. And the actions available are buy X. The preconditions of buy X are at store, add list is have X. The other action is go XY, precondition is at X, delete list is at X, add list is at Y. Now, when we go from a home to the store, we created, so initially suppose we are at a situation S. When we go from the home to the store, when we go from the home to the store, we are at a new situation S prime. And in S, as I said, my son is at home, the store sells bread, my age is 38. In the new situation S prime, these propositions continue to hold. Now, we want to know how we can efficiently represent everything that has not changed. And strips provides a good solution for simple actions. Strips just says that apart from those propositions that we have listed in the add list and delete list, the rest of the propositions are maintained as it is in the next situation as in the previous situation. Now, the ramification is that suppose as a result of executing the action go to the store, suppose I am now in Gold Bazaar, the number of people in the store went up by 1, the contents of my pockets are now in the store. So, this is the actual effect of my action. Now, do we have to encode all these when we describe the effects of the action? In strips, you do not really have to infer all these things, you do not have to specify all the effects of the action which can be inferred by some other technique. For example, the fact that the number of people in the store go up by 1 if I go to the store, that can be handled by some rules. Primitive facts like at home persist between states unless we specifically change this by executing a go action. Inferred facts are not carried over and must be re-inferred. So, suppose the store currently has 5 people. If I go to the store, the number of people in the store becomes 6. So, these things are not specifically need not be mentioned in the add and delete list, but they can be inferred. And this use of rules avoids making of mistakes. Now, let us see how planning can be looked upon as a search problem. We are given a representation of the initial state, a set of strips operators and a goal condition that we wish to achieve. And as we mentioned, the planning problem means that we have to determine a sequence of actions which when applied to the initial state yields a state which satisfies the goal. Now, we can look upon this as a search problem where the initial state is known to us. The actions are the possible operators that map a state to other states. So, we can have a state space graph and the goal is satisfied by any state that satisfies the goal. So, suppose my initial state is at home, not have banana, not have money, right? And the actions that I can execute is, let us say, go store, go office, go movie, go bank, cook dinner, and so on. And as a result of the go store action, we will have the initial state will get transformed to a different state, and from this state again the different actions can be applied. So, we see that we have a state space formalism, and we can search in this tree until we get a state where the goal conditions are satisfied. So, planning is actually, the planning problem is actually a search problem. So, this is another example of the planning problem. We have this initial state in the blocks world where B is on top of C and A is on the table. If we execute the action move A, B, then we get to this particular case. A is on top of B, B is on top of C. If we execute the action move B, A, then we come to this state. If we execute the action move B table, we come to this state. If from this state we execute the action move C, A, we get to this state. Suppose our goal is represented by on C, A. Now, we notice that in this state on C, A is true. So, this is a state which satisfies the goal condition. So, this is a goal of the planning problem. So, the planning problem can be cast as state space search problem, and we can detect whether a goal situation has been achieved. But the main problem in casting the planning problem as such a state space search problem is that the state space can be very large, because the number of actions that we can execute in a state may be very large. So, the state space may really explode. That is, the search tree is generally quite large. Also, the description of the planning problem suggests a logical structure of the problem, because you see, each action typically only affects a small set of propositions, and actions depend on each other. Planning algorithms have to be designed to take advantage of this special nature of the representation. Now, normally we can start from the initial state and we can do a search in the forward direction, which is known as forward state space search. That is, forward state space search means you search from what is known in the initial state and apply operators in the order that they are applied. An alternative to forward state space search is backward state space search. In backward state space search, you do the search the other way. That is, you search from the goal, you start from the goal state and you try to find out the actions that would have led to such a state. So, you consider the actions in reverse and the states in the reverse direction. So, you search from the description of the goal and identify actions that help you to reach the goal. In a forward search, typically the branching factor can be extremely high. All applicable actions have to be considered from each state, and typically they may include many actions which are irrelevant. Suppose my objective is to bake a cake. Now, going to a movie is an action which I can perform at the initial state, but whose effects are irrelevant to the goal of baking a cake. So, search is very inefficient. If we have a forward search, typically search would be very inefficient unless we use a very accurate heuristic. If we do backward search starting from the goal, this allows us to consider relevant actions. However, backward search also we can have some actions which are irrelevant, in the sense that we could not have arrived at their preconditions starting from the initial state that we have. But usually backward search, actually backward search is also called regression planners. So, planners which do backward search are called regression planners, in contrast to the forward search planners which are called progression planners. So, regression planners typically have smaller branching factor, and for most problems they have a more focused search space than planners that search in the forward direction. However, both backward and forward search may lead to a lot of irrelevant consideration of a lot of irrelevant action. So if you really want to make the planning problem efficient, you need to employ very good heuristics. And in the subsequent lectures, we will look at heuristic planners and the sort of heuristics they employ. So with this, we will end today's lecture. Today's lecture has mostly been on a description of an introduction to the planning problem. So the questions that we have for today's lecture is question number 1. Explain how planning systems differ from classical search techniques. Question number 2. Formulate the Block's world planning problem. So take a particular description of an initial state of a Block's world problem, take a description of the goal state and represent the initial state, represent the goal state, list out the possible actions in the Block's world. For each action, you give the precondition list and the effect list, and then you can take an example, this example problem, and draw the search space corresponding to this problem. With this, we end today's lecture. Thank you.